Welcome back to the Taurus Report, the bull in the china shop of cosmology. Today we are going to break general relativity. General relativity is called general because it generalizes the theory that Einstein came up with in special relativity. And what was that about? That was developed at a time when many physicists were trying to explain the results of the Nicholson-Morley experiment. In the late 1800s, Maxwell had discovered that light was electromagnetic radiation. It was a wave. And when you have a wave, it's normal to think that there must be some sort of medium that is wobbling back and forth. For instance, if we see waves rippling across water, water is the medium, and we see the ripples in that medium as the wave travels. So everyone assumed in the late 1800s, when Maxwell discovered that light was a wave, it was natural to assume there was some kind of medium that was wobbling as light traveled. And this medium was called the ether. So the Nicholson-Morley experiment was set up in such a way as to try to detect that ether. And here was the way the Nicholson-Morley experiment was set up. The idea is that there would be some sort of universal rest frame, and in that universal rest frame, the ether would be at rest, and that is the medium by which light would be traveling, like ripples in water or sound waves in air. The ether would be providing the medium by which light waves travel. Here is the way the Nicholson-Morley experiment was set up. You have a light source here, and there's going to be two different paths. One in the longitudinal direction, this way here, and one in the transverse direction, this way. So the light source starts from the same place, and it's going to travel to two different mirrors. One mirror is attached to the apparatus. It's out here at some longitudinal distance, this mirror, and the light will go to it and come back longitudinally. Then another mirror is put the same length but transverse, and the light is going to travel to that mirror and back, and both those distances are the same. Now, the one in the longitudinal direction is co-moving with the light source in the longitudinal direction, and the one in the transverse direction is co-moving parallel to the light source. So let's look at the longitudinal path. Again, the light source is moving relative to the ether, and the mirror is co-moving with it. So the light must travel all the way along here, hit the mirror, this mirror, come back, and then it hits this half-silvered mirror. That's what this slanted line is a half-silvered mirror. And so some of it will be reflected and then come to the detector here. That's the longitudinal path. Then the transverse path, light travels along, hits the half-silvered mirror, travels up to this transverse mirror, is reflected back, passes through the half-silvered mirror again, and so on to the detector. Now, to make a long story short, if there was an ether, and if light traveled at a set speed through that ether, then what we would expect at the detector is we would expect the transverse wave to have traveled a shorter path, and so the transverse wave should arrive first, and the longitudinal wave should arrive second. But what actually happened is that they arrive at the same time. and the Michelson-Morley experimenters, they could not explain this. How could this happen? It sort of disallowed the idea of the ether. It sort of proved that there was no ether. And so there were various ways of trying to account for this. Now, Lorentz, he's the one who came up with the Lorentz transformations. He said that maybe the whole apparatus is shortened when in the direction of travel, so that this length of the apparatus as it travels is shortened. And that is why, and it is shortened proportional to its speed, which is very interesting. Please remember that. Shortened in proportion to its speed such that you get the arrival here at the same time. Now, Einstein was later to resolve this difficulty in a different way. What Einstein said was that all of space, for an object traveling, all of space is shortened in the direction of travel. And there was sort of a disagreement between Lorentz and Einstein about this, where Lorentz was saying just the apparatus that is moving is shortened in the direction of travel. And Lorentz was working on an explanation for this based upon electromagnetism, because by coincidence, electromagnetism also is dependent upon velocity. So Lorentz was saying this might be due to electromagnetism somehow, where any object that is traveling relative to the ether, any object that is traveling is shortened in the direction of travel. Well, Einstein said no. Instead, motion, and later we'll find out mass has an effect on this as well, motion causes a shortening from the perspective of the moving object. There is a shortening of all of space in the direction of travel. Now, as we proceed, we are going to see that I am proposing that Lorentz was correct and Einstein was wrong. I am going to propose that, in fact, as an object travels through space with a velocity relative to the universal rest frame, I'm resurrecting that idea of a universal rest frame, and I will get to that later. I will explain how that works and what it is. But as an object travels with any velocity relative to the universal rest frame, the object is shortened in the direction of travel, and I am going to claim that all of space from the perspective of that object is not shortened, that instead just the object itself is shortened. So I am going back to Lorentz's idea. But why was Lorentz's idea discounted? Why was it set aside originally to begin with? And the reason is that Einstein, with his geometric approach, was able to explain several other phenomena that Lorentz could not explain. And so Lorentz's view was abandoned in favor of Einstein's views because of that fact. Einstein's special and general relativity makes several predictions that Lorentz's view was not able to make. Now, we will get into explaining those as well coming. So what was Einstein's general and special relativity able to predict that Lorentz could not predict? There were several things. First, Einstein could account for the precession of the orbit of Mercury. Secondly, Einstein could account for time dilation in two different contexts. One was time dilation by an object that is moving. So any object that has a velocity, time slows down relative to that velocity. And time also slows down in a gravity well, and Einstein was able to explain that. In addition to time dilation, Einstein was also able to explain the increase of relativistic mass. When an object is traveling at a velocity, the faster velocity, the momentum increases in a way that's sort of like the object is becoming heavier, like the mass of the object is increasing. We don't like to characterize or explain it that way, so we talk about it in terms of relativistic momentum. But Einstein could explain with his equations all of those things in addition to accounting for the results of the Nicholson-Morley experiment. And because Einstein was able to do that, his view about length contraction prevailed over Lorentz's view. Let us look at time dilation and length contraction first from the standpoint of special and general relativity. And then after that, I will explain how these things need to be adjusted and changed in the presentation of CGC. As a reminder, if you would open a browser and just type in torus report, all as one word, .com, and hit enter, then that should take you to my site. And if you scroll down, you can see that you can access the torus report on Spotify, YouTube, and also Facebook. And you may also download a paper on CGC there. So if you click on that and download the PDF for CGC, then you will see my paper. And if you scroll all the way down to, let's see, what section are we in? We're in section 12.2, where we're talking about time dilation in relativistic velocity. I write here about a very famous experiment which was done at Mount Washington by Frisch and his colleagues in 1963. And this appears in textbooks to illustrate time dilation. And the way it works is like this. Muons come streaming in from outer space all the time, and they have to go through our atmosphere, before they arrive at sea level. So they did a little experiment at Mount Washington where they put a detector at the top, and then they put a detector at sea level. And so they detected how many muons existed at the top and how many muons existed at the bottom, because muons have a short half-life. So however many are detected here, we would know through calculation, and I go through the calculations in the paper if you want to read it, we would know how many should arrive at the bottom. And if we get a different number, so without relativity, we would expect a certain number to arrive at the bottom, and instead, a lot less arrive at the bottom, which means that from the perspective of someone at rest here who's observing all this, time must slow down for those muons. So time slows down, and so what ends up happening is more of them arrive at the bottom than we're expecting. In other words, we would have expected a lot more of them to have decayed. And because the number we're expecting to decay did not decay, we end up with more than expected at the bottom, and that means that time must have slowed down. Now, traditional special and general relativity, if we switch to the perspective of, let's suppose there's someone traveling along with the muons. Okay, someone is traveling along with the muons. Why do they detect less decay than expected? Because from their perspective, their time did not slow down. And so why would they experience less decay than expected? And according to special and general relativity, as they travel, the length of all of space contracts. And so for them, the mountain is shorter. And so they actually travel a less distance. And so because they travel a less distance, they experience less decay. And this raises a very important point, difference between general relativity and CGC. Length contraction in general relativity means that for an object at velocity, all of space from the perspective of that object is compressed in the direction of travel. Under CGC, only the object traveling itself is compressed in the direction of travel, and velocity is relative to a universal rest frame. There is a universal rest frame, and there is also a physical explanation for the contraction, and it does not rely simply upon geometry. In general relativity, mass and velocity are linked. Mass, space, velocity, time are linked in a geometrical description of a continuum. And that is not the case at CGC. So length contraction is different. Also, time dilation. In general relativity, time is portrayed as a sort of, you might think of it as a fourth dimension of space. And so space and time are linked in a continuum. And mass is linked with all of that in a geometrical sense. So time and general relativity is sort of like a continuous dimension. In CGC, that is not what time is at all. Time is not a continuum, it is not a dimension, and it is not linked with space in a continuum. Time instead, under CGC, is defined as the record of change. And so time is the record of discrete changes. And when you have time dilation, or let's say time slowing down, that is actually due to a physical cause wherein at the subatomic level, all subatomic processes are slowed down. It's sort of like the idea of putting bacteria in the refrigerator. Something under refrigeration, the molecules and various constituents of that object just move slower. And so time is sort of, for that object, is objectively slowed down. In CGC, time dilation is attributed to a physical cause, which I will go into, and time dilation is actually due to a slowing down of physical processes, where physical processes are inhibited, and so things are actually moving slower for the object that is subject to time dilation. So let us get to it. How is CGC going to explain all of these things using going back to Euclidean space and presenting physical mechanisms for these things rather than relying on the geometry of a non-Euclidean continuum? So going back to the paper, first off, about length contraction, jumping back to this length contraction, as far as for an object at velocity, I am going back to Lorentz's expression, where here we see this L sub 1 represents the length of the object as it's traveling at velocity, and L sub 0 represents the length of the object at rest. So if the object starts moving at velocity, it is going to be the length will be multiplied by a decimal that's less than 1 that is based on the Lorentz contraction, the Lorentz factor here, where you make a factor where the object's velocity, u is the velocity of the object with respect to the universal rest frame, and c is the speed of light. So what this means is that the object itself will be shortened. Space is not shortened. And this is due to electromagnetic interactions with the surrounding medium as an object travels. It becomes shortened. Lorentz was working on this and abandoned it after Einstein was able to explain all the other phenomena, which we'll get to. So I am returning to this idea of length contraction of an object moving at velocity. Now, the next thing that I would like to talk about has to do with two things: time dilation and the deflection of light around a gravity source. I posit two, well, it's a hypothesis. I'm proposing that neutrinos have several properties that have not been proven yet, but I have come up with several experiments by which this idea can be tested, and I will get to those proposed experiments in a later episode. But here are the three properties I'm proposing for neutrinos. Property number one is that they are tremendously attracted to masses. So any large mass like the sun or the earth is going to attract a higher concentration of cold neutrinos. Now, I'd like to differentiate between hot neutrinos and cold neutrinos. In astrophysics jargon, when we say something's cold, we just mean it's not traveling very fast. If we say something's hot, we just mean it's traveling very fast. With current technology, the only neutrinos, because they are so weakly interactive, the only neutrinos we can actually detect are hot neutrinos. They have to be traveling at a very high velocity. And then when they impact, even then, we can only detect a super tiny fraction of them. And so hot neutrinos are the only things we're able to detect right now. If there are tremendous quantities of cold neutrinos surrounding any mass, as I am proposing, we don't currently have the technology to be able to detect those cold neutrinos. So that is property number one that I'm proposing. Neutrinos strongly attracted to mass. Property number two, I claim that neutrinos do refract light at sufficient concentration. If you have a high enough concentration of neutrinos, then they are going to refract light. The final property that I'm proposing for neutrino concentrations is that they inhibit all other quantum processes. So any sort of subatomic or molecular atomic process going on, I am claiming that neutrinos inhibit those. So if you have a high concentration of neutrinos, the effect that we would observe at a macro level would be time slowing down. Time slows down because just like putting bacteria in the refrigerator, the coldness inhibits change, and whenever you inhibit change, you are slowing down time. So I am saying that a high concentration of neutrinos slows time down. Let us put all of this together. I am proposing that there is a universal rest frame, and that universal rest frame is the frame wherein the CMB, the cosmic microwave background radiation, is not Doppler shifted. Since that radiation arrives from all directions in the sky, and since it is presumed coming from the most distant regions, if we take a frame where that CMB is not Doppler shifted, for the entire universe, that would be the most sensible rest frame to assume. And so I am assuming that most neutrinos that are not being actively acted upon or have not been accelerated for some reason or are not being attracted to a mass, most neutrinos in the universe, that frame would also find the highest percentage of cold neutrinos in that frame. So let us look at adapting special and general relativity based on everything I've said thus far. When we have a mass traveling at velocity, that mass is going to increase because electromagnetic forces increase at velocity. In other words, if you accelerate any charge, and any mass is made up of charges, if you accelerate any mass, the electromagnetic force will increase proportional to the velocity. And this is well known. Now, if mass and gravity are related to the electromagnetic force, as I'm claiming, then it makes perfect sense, according to the laws of electromagnetism, it makes perfect sense that an object traveling at velocity would act as if it is more massive, because mass is based upon electromagnetism, according to what I'm saying. So an object at velocity is more massive because of that velocity. Also, an object at velocity is going to encounter more neutrinos per unit of time than an object at rest. And here I'm talking about an object at rest or at velocity far from any major mass. So I'm talking about like a spaceship traveling interstellar space, so far away from any star or far away from any planet, like far away from any giant mass that would attract neutrinos. As the object travels at increased velocity, it is going to encounter more of the cold neutrinos in space. And if neutrinos inhibit quantum processes, as I'm claiming, then time would slow down for that object for the simple reason that quantum processes are slowed down by neutrinos. So that is an object at velocity. Now let's look at an object in a gravity well. In a gravity well, you have within the nuclei of atoms and the electrons orbiting the nuclei, you have proportionately a lot more charges. And so the object is more massive for the simple reason that there's more charges there. And so mass increases and the electromagnetic force increases because you have more objects there with charge. And so it makes perfect sense that gravity increases in that context. Now, time slows down in a gravity well because, according to what I'm saying, any massive object attracts huge quantities of neutrinos. The neutrino concentration goes up, and if neutrinos inhibit quantum processes, as I'm claiming, then time would be slowed down in a gravity well. And so, in both contexts, relativistic travel at velocity and in a gravity well, you have increase of mass and time dilation, and there's a good reason why that occurs. Looking again at my paper on CGC, this chart in section 14 here, this chart kind of sums up the connection. Okay, so this chart is in section 14.3. So at relativistic velocity, since gravity is an EM force, high velocity equals increased EM force, and high velocity also equals more cold neutrino encounters, and so you get time slowing down. In a strong gravitational field by a massive object, you have more particles, which means more EM force, which means gravity increases. Mass also attracts more neutrinos, and you have, since there are more neutrinos, there's more neutrino encounters, and time slows down. Now, this is very important because this explains, if this is all true, and again, I will in later episodes explain various experiments by which this idea can be tested. This can be experimentally tested. Now, the experiments are going to be extremely expensive, but it is testable. So why this is so important is that this explains why Einstein's equations work, even though they're wrong. Well, I shouldn't say the equations are wrong. The equations are not wrong. The conception of geometry of a space-time continuum that is sort of behind the equations, I'm saying that conception is wrong. Space is Euclidean. It does not stretch. It is not warped. But Einstein's equations work. And the reason they work is because they correctly make a connection between travel at relativistic velocities and phenomena inside a gravity well around a massive object. There is a fundamental connection between those two things, and Einstein's equations make that connection, and that's why Einstein's equations work, even though the conception of non-Euclidean space behind those concepts, that conception is completely wrong. Generations of people have pointed out that Einstein's conception was self-contradictory and so obviously had to be false. And anyone who says that, they're ignored or laughed at or ridiculed for the simple reason that his equations work to predict a lot of physical phenomena. And if the equations work, then it explains why people who point out the logical contradictions get laughed at. It's basically like, well, the equation works. You're just silly because you can't accept that. And in truth, I'd like to give you like one example. Okay, so if you have two spaceships that pass by each other going in opposite directions, let's say. Now, according to Einstein's relativity, the way that he frames it, the guy on this top ship, he would say that the other guy's clock is running slower, okay? And the guy on the bottom ship, he would be saying that the top ship's clock is running slower. Now, obviously, that's a logical contradiction. And GR apologists, they get out of it by saying, no, space and time are always defined from the perspective of the observer. So it makes sense that two different observers would say a contradictory thing. And so they claim that that's not a logical contradiction. And I claim that it obviously is a logical contradiction, and with all of your verbiage, you're just saying that you're okay with the contradiction. Now, what would CGC say is happening? Okay, CGC would say there is an objective rest frame, the frame wherein the CMB is not Doppler shifted. That is the objective rest frame. And for any object at rest, time would pass fastest for an object that is at rest to the universal rest frame and is far away from any gravitational source. So time would pass the fastest for that object. And time would pass slower for you because of two different potential reasons. One would be is if you start moving at velocity to this universal rest frame, or if you get near a gravity well, then time would start slowing down for you. Okay, so time slows down as you travel at velocity compared to the universal rest frame, or if you get near a gravity well. And approaching it in this way means that there are no logical contradictions at all. So I am going to elaborate a little more on this in future episode where I speak primarily about, so I can suppose all these things about neutrinos and make all these proposals, but how do I go about proving it? So I would like to share in a future episode various experiments that I am proposing that could be done to both disprove general relativity and also potentially disprove my theory. So some of these experiments might disprove both. Or general relativity might be left standing while my theory is disproved, or all the way around. My theory might be left standing while general relativity is disproved. In any case, I'm going to be proposing some solid experiments that can be done to test this idea. In the next episode, however, I'm going to do somewhat of a digression because Einstein's relativity has a lot to say about what a black hole, well, I should say it is very relevant to what theorists might say a black hole is and its various effects, and what we're seeing from the LIGO apparatus. And so in my next episode, I want to concentrate on those two topics, what we're seeing from the LIGO apparatus, and what would CGC say about what a black hole is and what its effects are. So thank you very much for watching the Torus Report this week, and I look forward to seeing you next week. Bye-bye for now.